Okay, so they have a continuous energy spectrum. Now, why is that? Well, after a lot of scientific experiments, they determined that in a beta decay, there is not just a beta particle, there is another particle given off, which is a massless and chargeless particle called a neutrino. So in the case of a beta negative decay, the particle emitted is an anti-neutrino. Okay, and in the case of a beta positive decay, it's a neutrino. So when the beta negative particle is given off, a part of the energy is taken away by the anti-neutrino over here. Okay, so this anti-neutrino might take either this much energy, or in another decay it might take more energy. Okay, leaving the beta negative particle with the remaining. In some decay it might take all of the energy, almost all of the energy here, leaving the beta with little bit of energy, right? And in another type of decay, you might have the neutrino just taking a bit of it, and the beta negative taking the rest of the energy. So therefore you can see that the beta particle can have energies ranging from, well, almost from 0 to all the way to the total energy being released in this decay. So therefore beta negative particles will have a continuous spectrum. Same thing for this case as well. Okay. So that's a beta negative decay. A beta positive decay is pretty similar when you have a proton disintegrating into a neutron and also a positron. Okay, the proper way of writing this would be okay, and like we just mentioned, we have a third particle given off. In this case there is a neutrino. Okay, so this is a beta positive decay. Okay, so we've talked about gamma rays already, so we've covered all three. Now, again, you must keep into account that an alpha particle decay might be accompanied by a gamma ray, and also a beta particle decay might be accompanied with gamma rays. 7.2.4 basically mentions the biological effects of ionizing radiation. So you can go through this. It's a little theoretical, not heavily tested in the exams, but it's good for the students to know how an ionizing particle can destroy DNA cells within your body. So this is something you can go through the students with. Again, there's a table here which has not really been tested from my experience, which shows the relative dosage of radioactivity which are unsafe. 7.2.5 explain why some nuclei are stable, why others are unstable. So over here, you can see from this table over here, the excess of neutrons over protons as we go above in the proton number. So you can see that until about proton number 20, you have the same number of neutrons and protons. Okay, but after that it goes on increasing, and the reason has been stated over here, which basically states that if you have protons, okay, so you have protons in a nucleus. So we talked about how the strong nuclear force is what keeps these protons together, right? But this proton is going to repel all these protons. Okay, so when a proton here repels the protons here, so basically the strong nuclear force only affects at close ranges, but the electrostatic repulsion will affect even between these two protons. So in order to make this nucleus more stable, what happens is that there are neutrons in between to fill up the gap, so the electrostatic repulsion reduces. And as the size of the nucleus increases, you need more of these neutrons. So above proton number 20, the number of neutrons starts to exceed even more. But even then, the nucleus starts to become more and more unstable and goes into a high energy state as and when more particles are added into the nucleus. Okay, so these unstable nuclei then fall to a stable state by either giving off a chunk of their nucleus as a radioactive decay. Okay. 7.2.6 7 and 8 have been chunked together in one portion called half-life. Half-life is basically dealing with the rate of decay, rate of radioactive decay. So the formulating equation for this, basically, which we'll go into more detail in the HL topic of radioactivity, is this. The rate of decay is proportional to the number of radioactive nuclei. Okay, so the more the radioactive nuclei, the faster the decay would be. Okay, and if you see this, if you see a graph of how the rate or the percentage of, okay, either the rate of decay or the number of nuclei present here, okay, with time, how this changes would then be like that. Okay, so over here the rate of decay was high. That's a negative sign because we are talking about decay, so the gradient would always be negative. The gradient here is high, then as the number of nuclei starts to decrease, the gradient starts to get lower and lower. Okay? Okay, and how is this measured? Activity is measured in, radioactivity is measured in becquerel. So becquerel. Okay, BQ, which is 1 becquerel is basically 1 disintegration per second. Okay, so yeah, this will be discussed in much more detail in the HL portion when we go into the radioactivity, the half-life and the constant, radioactivity constant and stuff. Okay, so that pretty much covers 7.2. From here on we'll move on to nuclear reactions, fission and fusion. Okay, 7.3 is nuclear reactions, fission and fusion. The numerical concepts in this are a bit hard to grasp for some of the students, so you want to be very crystal clear on the concepts over here. So first part is just description of transmutation. Transmutation is basically one chemical element changing to another. Okay, and this could also include like your radioactive decay that we just covered. Artificial transmutation is artificially inducing a nuclear reaction caused by the bombardment of a certain particle. So there are some examples of that where particles are being bombarded here, for example by alpha particles or by a neutron. Okay, so that is an example of artificial transmutation. Okay, next is the definition of an atomic mass unit. Atomic mass unit is defined as 1U, which is approximately the size of a proton. So 1.66 times 10 to the power minus 27 kgs. Okay? So you can, it's easier to work with this so that you don't have to write this cumbersome number again and again. Next portion is Einstein's energy mass equivalence. So Einstein postulated that any mass has a corresponding amount of energy. Okay, so for example, if there's a change in energy of delta E, okay, there is a corresponding change in mass delta M. Okay. And how are these two related is via this equation, delta E equals delta M c squared. Okay, where c is the speed of light. Okay, now when a mass is at rest and has a rest mass m naught, okay, so its corresponding rest mass energy, okay, is given by E equals m naught c squared. Okay, so how is this related to what we're doing? Suppose there is a nucleus, okay, which has 4 constituent nucleons. Now this nucleus, these nucleons are held together tightly. Alright. Now if I had to break these nucleons apart into the individual constituents, okay, I have to feed in a certain amount of energy. Okay, this much energy must be fed in order to break it into its individual constituents. Now the converse is also true. If these individual constituents were to combine together to form a nucleus, okay, there would be a certain amount of energy released. Okay. Now, by this equation, we know that if this energy is released, the mass of the combined nucleus here must be less than its individual constituents. Okay, and this mass is given by delta M. Okay, and delta M is related to the energy released via c squared. Now, the energy released, or over here the energy given in order to break it apart, so you can define it in either one of the two ways. I like to define it as the energy released when the individual constituents are combined to form the nucleus. This here energy release is called the binding energy. Okay, and the correspondence defect in mass. Okay, the defect in mass, because the combined mass is smaller than the individual masses. This here is called the mass defect. Okay. Now, so these are basically defined over here in page 15. So how binding energy is related to mass defect. Now, notice that binding energy, when we talk about the binding energy of a nucleus, okay, it's not some energy that this nucleus possesses. It's an energy that I need to supply in order to break it apart. So it's actually a lack of energy. Okay, so you must, so over here in bold it's mentioned that the larger the binding energy, the larger the energy needed to take all the constituent nucleons apart. Therefore, a larger binding energy usually means that the nucleus is more stable, right? So mass defect. So the relation between mass defect and binding energy is given here. Now, although the larger the binding energy, the more stable the nucleus is. That's one way of putting it. But how about if this nucleus had a lot of nucleons? So maybe it has some 200, 300 nucleons. Obviously, the amount of energy that I need to put in is more because of the number of nucleons. But does that mean that the nucleus is more stable? That may not be the case, because over here I might need to be putting in more energy per nucleon. Okay, so a more standardized way of measuring stability of nuclei is to take the binding energy, okay, and then divide it by the number of nucleons. And what you get is the binding energy per nucleon. Okay, so now binding energy per nucleon is a good method of measuring the relative stabilities of different nuclei. Now, if you see a graph of the binding energy per nucleon of all the elements in the periodic table, that graph is given at the bottom of page 16 and is quite important. You can see that the binding energy per nucleon is low for smaller nuclei, and it rises up very sharply from the nuclei over here, like helium. You have hydrogen, deuterium, helium-3, tritium, and it goes up over here all the way, and it keeps on increasing until iron. Iron has the highest binding energy per nucleon, which means that it is the most stable element. Okay, it's the most stable nucleus. Now, after iron, it goes on decreasing again, but not at such a sharp rate. So until we reach the higher end nuclei like uranium-238, etc. So what this means is the bigger nuclei like U-238 are unstable and therefore will disintegrate or undergo fission, for example, in order to form two daughter nuclei which are of a higher binding energy per nucleon, which are more stable, of course. And also the smaller nuclei like hydrogen and helium, they can undergo fusion in order to form a more stable nucleus. And you can see that since the left side of the graph is much more sharp, fusion will definitely release much more energy as well.